Okay, so in the fifth example they introduce vectors, and in general vector information given in vector form is generally more straightforward because you haven't got to worry about components, you haven't got to worry about UX's and UY's because it's already split into horizontal and vertical components. What makes this question a bit trickier, if we read through it, at time t equals 0, a particle is projected with a velocity of 2i meters per second from a point with position vector 10i plus 90j. With all the previous questions, the origin where we've been measuring position from has been the point of projection. With this particular question, I'll set it up as a diagram now, that's not the case. The point of projection is relative to an origin at some other point. So if we consider what's happening here, which is similar to all the previous ones, we've got this particle projected with a velocity of 2i, so there's no vertical component, so u equals 2, 0, and that's going to fall to some position here, which we don't know, and it's going to reach that point at t equals 4. The point of projection has got a position vector 10i of 90j. So what that is saying is that relative to some origin, perhaps over here, this point is going to be 10 in that direction and 90 in that direction. So the position and position vectors, rather than using s, they tend to use the letter r. So I'm saying there r and then a suffix. Rt equals 0 is going to be 1090. Oh god, that shouldn't be a fraction, it's a vector. So 1090, and we know that 4 seconds later this is going to end up over here. So its position at t equals 4 is there. Now the calculation that we're going to do using s equals ut and so on gives us the displacement from the point of projection to where it is 4 seconds later. So this here is what the calculation is going to perform, is the displacement. That's the movement between t equals 0 and t equals 4. Now, in vector terms, in order to work that out, in order to put that as an equation, what we have is we've got the position at t equals 4 is going to be the position at t equals 0 plus the displacement. So the position at t equals 4 is what we want. That's equal to the position at t equals 0, which is 1090, plus the displacement. So this now is our s equals ut plus half at squared. U is 20 plus a half, oh, and I've forgotten the t again. So ut 20t plus a half, ax is 0, ay is 9.8, t squared. And I know that t equals 4. So I have 1090 plus, do that again, so the 1090 is moved down, 20 times 4 is written there. I've evaluated a half times minus 9.8, but I've still got the 4 squared in. So that's 10. Oh, it's not a fraction. I'm sure you're going to get wound up by doing that as well. I write fractions more than column vectors. So 1090 plus 80 for that one. And for this one, it's going to be 0 minus 4.9 times 16, which is 78.4. So r at t equals 4 is going to be 18, and 90 minus 78.4 is 11.6. Now we're writing in column vectors. Questions given it in terms of I and j, so it's just good manners then to write 18i, and the 11.6 rounds to two significant figures, plus 12j 2sf. If you forget that rounding to two significant figures in an exam, they'll penalise you once over the paper. So don't get stressed about it. What I would always suggest you do is to round your final answer, but make sure you've written down prior to that what the unrounded values are that you're using. So that one's a little bit trickier just because of the fact that we've got to work out its position relative to an origin rather than using the point of projection as the origin.